This is Professor Derf Seitz. Statistics, zero inflation. How should we view things that are infinitely close to zero? How big, quote, is the infinitesimal? Are zero and its infinitesimal neighbors being inflated? Here's a picture I took of an inflated zero. Does the interval 0 to 1 open on the left contain a smallest number? Many beginning college level mathematics students of all ages say it does have a smallest number. When asked what that number is, a frequent answer is 0.01, which is 1/100th. When countered with 1/1000th being smaller and yet in the interval, they often quickly reply with, add more zeros. This interval in question, which is open on the left, this is interval notation, consists of all real numbers x such that x satisfies this relationship. It's strictly greater than 0 and less than or equal to 1. The square bracket indicates inclusion of the interval endpoint, the parenthesis exclusion. Suppose S is the smallest number in this interval. Since S has to be greater than 0, since it's in the interval, it is at a positive distance, S, away from 0. Then if we look at S divided by 2, that's also greater than 0, and it's a number smaller than S in the interval, which would contradict our assumption that S is the smallest number in the interval. Therefore, there is no smallest number in this interval. There are infinitely many, infinitesimally close numbers descending towards 0. How big is a point? Many beginning college-level mathematics students of all ages say a point has a size. When asked what that size is, a frequent answer is also 1/100th. When asked what are the units, a frequent answer is inches. When asked if that is big enough to see, a frequent response is, then it must be bigger. A point with coordinates x, y in a two-dimensional space represents a unique location or position. Such a point has 0 size. If a point had a non-zero size, it would have a diameter greater than 0 and would occupy more than one location. There are infinitely many, infinitesimally close, 0-size points in two-dimensional space. Ditto plus for three-dimensional space. Here's a picture I took, a little bracket that looks just like a little infinity sign. And you can view this either as infinity of space or the infinity of smallness. Micro, smaller than micro, infinitesimal. Can a runner ever finish a race? To finish a race, a runner must cross the finish line. Suppose the runner is 1 meter from the finish line. It will take a non-zero time, say t1, to go half the remaining distance, half a meter, t1. It will take another non-zero time, t2, to go half the yet remaining distance. You can continue this reasoning ad infinitum. The time remaining is t1 plus t2 plus t3 plus t4 plus forever. You can add in smaller and smaller times, infinitely many of them, as the time remaining. Yet the runner quickly crosses. Again, we have infinitesimals, infinitely many of them, being passed like that. Let's take a little excursion into the infinitesimal. The following series converges to 1. What does that mean? This series, this is a summation from n equals 1 to infinity of 1 over 2 to the n. Written out, it's 1/2 plus 1/4 plus 1/8. You see there, the denominators are doubling, 1/64, etc. And this is kind of like the runner. If they're halfway to the finish line, you add another 1/4, you get half more and another 1/8, and it's very similar. And the sum, this infinite sum, approaches, can get as close as you want. It's called converging to 1. And that makes sense. We'll see a picture of it in a minute. This series here diverges to infinity. It's the series, the summation of n equals 2 to infinity of 1 over n. Written out, it looks like this. 1/2 plus 1/3 plus 1/4 plus 1/5 plus, you get the idea, plus 1/8. If you add all those together, it can keep going and going. It does not converge. It gets infinitely large, without bound, infinity. Notice that all these fractions are getting smaller and smaller. You're getting smaller and smaller things in both cases. But in this case, it converges to 1. In this case, it diverges. Infinity. How is this possible? We'll look at this now to understand how we have not natural abilities to really appreciate the infinitesimal or the infinite, because we're finite beings in a finite thinking mode. Here's a numerical analysis. In a Microsoft Excel spreadsheet, I looked at this series here, the one that converges, and the other series here, the one that diverges. You look over here, look 1/2 and 1/4 and 1/8. Look at this divergence series. This series on the left is part of this series. You see the 1/2 here, the 1/4, the 1/8. It's part of this series. And the important point is that this first series, the denominators are doubling, which is exponential growth. Exponential growth is the fastest growth possible. It's the kind of growth that makes nuclear explosions happen, where there is an exponential number of very small energies, and the exponential sum of them becomes unimaginably huge. Let's look at this green series here. We start out with 1/2, which I color-coded like the convergent series, and then 1/3, and then 1/4, 1/5, 1/6, 1/7, and 1/8 from this series, 1/9, 1/10, all the way over to 1/16. Now look to go, now there's a whole lot more till you get to 1/32. And there's a whole lot more until you get over to 1/64. So what's happening here is because the doubling effect of the terms in this series means that between each one of them in the series on the right, there are more and more terms. And how many more? Exponentially increasing numbers of terms. They're getting smaller and smaller, infinitesimally small, but they're increasing in number exponentially. So down here we have denotes the sizes of the green subset fractions are steadily decreasing towards 0. The cardinality, or number of members, of the green subsets is growing exponentially. Here we continue going off to the right all the way through 1/64. And this spreadsheet takes sums of each of these subsets. The 1/3 is just 1/3, 0.333. It's an infinitely repeating rational number. Between 1/4 and 1/8, those three add up to 0.5095. Between 1/8 and 1/16, these numbers here add up to 0.6004, rounded, of course, to 4 decimal places. After that, the next group, which there's more of them, adds up to 0.6465, and the next group, as we look over here, adds up to 0.6698. These are listed here, the subset sums. Notice that they're increasing. The sum of all the green subset member sizes is increasing without bound. It's increasing. This picture here, a view into the infinitesimal. Here's the interval between 0 and 1 on the number line down here. And there's some bars, vertical bars, following the colors of the rainbow. The first one's at 1/2. And then you move over a distance, that's a distance of 1/2 from 0. And you move over 1/4 more. You get over here, move over 1/8 more to the next one, 1/16 to the next one. So these vertical bars represent the converging series where the denominators are doubling. You can see that they're getting closer and closer together, approaching 1. And if you go on forever, this is just the first few, and they're getting very small. You continue, forever is beyond our comprehension, but if you just keep going and going and going, they're going to get infinitesimally close and infinite numbers of them. But the sum of them all, as you can see, is approaching 1, converging. Meanwhile, these black bars here, showed 4 of them, show the sums of the green subsets that are between the terms in the converging series. We looked at those in the numerical analysis on the previous page. So here's the subset between 1/2 here and 1/4, and they're just shown there where they, in what interval they're in, and their magnitude that was calculated in that numerical analysis. And notice it appears to be a linear increasing relationship. These sums of, there are more and more items and they're smaller and smaller, are increasing. And if we take this on forever, and closer and closer to 0, do you see what's going to happen here? They're going to get bigger and bigger, not smaller at all. And infinitely many of them approaching 1. And if you added them all up, well, they're each bigger than, this first one is 1/3, this next one is bigger than half. Things bigger than half, infinitely many of them, it diverges. So here we have sort of a dichotomy of infinities, a convergent and a divergent series present together. And it reveals to us that the infinitesimal is not something we're familiar with very much. It eludes us. Can this happen by chance? Cut out each square, there's 100 squares, and put the blue box on the perimeter here, the blue box, on the ground. On a windy day, go to the top of a tall skyscraper near the box and fling the 100 pieces up in the air. Can or will they ever all fall exactly in place by chance? Surprisingly, or maybe not surprisingly, to me surprisingly, many beginning college level statistics students of all ages say that given enough time and chances, this can and eventually will happen. Think about it. You're up on the top of a skyscraper on a windy day. You take these 100 pieces, fling them in the air. Think about how many tries it would take even for one of them to fall exactly in place, let alone all 100. Even with added constraints, when I change the problem, such as saying, well, now you have to have multiple back-to-back same-day successes. So twice in a row it has to happen. The answer is the same from some people. Given enough time and chances, this can and eventually will happen. Simultaneous events are events that occur or happen together. In mathematics, the probability of simultaneous events is the product of their individual fractional probabilities. Probability is a fraction between 0 and 1. So each probability is a fraction. As fractions multiply other fractions, their product rapidly approaches 0. Some probabilities are so infinitesimally small, they require scientific notation to represent them. Consider the probability of success for just 1 square. Then multiply that by itself 100 times. Can this happen by chance? This will never happen by chance. Could it be? Consider the scientific debate surrounding creation. Did it happen by chance or by design? There are multiple, very small probability, what are called fine-tuning, cosmic factors necessary to support life. The probability of all these factors occurring together is absurdly too small to allow for the chance model of creation. A few example fine-tuning factors: the sun, the distance from the sun, water, air, particular gravitational force, particular electromagnetic force. For all these had to be particular values: strong nuclear force, masses of various atomic particles. They all have to be very special values, and even their relationships have to be certain within certain bounds. Probabilities of these things is infinitesimally, they're neighbors of zero. Here, this picture that I took is a depiction of fine-tuning factors. Each of these sycamore tree seeds, bulbs, you can see the ones right here in the foreground, and then up in the higher parts of the tree, there are many of them, scores of them. Think of those as fine-tuning factors, all with extremely small probabilities multiplied together, infinitesimally neighbors of zero. Conclusion: in the realms of probability and possibility, zero inflation continues to affect our thinking and beliefs. We need to correct our greatly over-magnified view of zero and its infinitesimal neighbors.